So yesterday was all about entropy. Today is all about something called Gibbs Free Energy. And what we're going to get into with Gibbs Free Energy is this idea that is something important that we need to be able to kind of address. We talked a lot yesterday about the idea of entropy, this idea of energy distribution, microstates, disorder, however you wanted to kind of frame it up. But here's the problem. Entropy, as far as a construct, is not the easiest thing to quantitatively measure. Yes, we have standard molar entropies, and if we know the values going in, we can theoretically quantify that. But how did we get those values in the first place? And if I were looking to do any kind of mathematical work, how would I go about it? And so we know that the second law of thermodynamics tells us that for a spontaneous process, the entropy of the universe has to go up. Well, how does it go up is really the key question here. And so what we start with is this idea of, okay, well, how do I measure the entropy of the universe? Well, I can measure the entropy of the system, and I can measure the entropy of the surroundings. And if I put the two together, that is my entropy change overall. But we didn't really talk a whole lot yesterday about the entropy of surroundings. How do I quantify that? Well, I can quantify the entropy of surroundings by taking the enthalpy of the system, and the opposite of the enthalpy of the system divided by the Kelvin temperature would give me the entropy of surroundings. Okay, that's a start. Um, so how do I use that? How do I go further? Well, okay, if I put this together, the entropy change for the universe is equal to the entropy change for the system plus this change here. We're getting somewhere close. And so if we start to do a little bit of mathematical manipulation, what we end up with is something called the Gibbs free energy for the system. And the Gibbs free energy for the system gives us an idea of how do I combine the entropy of the system, the thing that I'm looking at, the chemical reaction, and the entropy of the surroundings and how those are affected. And what we need to remind ourselves of is that our processes of endothermic and exothermic, the directions of those energy transfers, because that delta H has a direct impact on or is affected directly by the entropy of the surroundings. Well, what that tells us is that, okay, if delta H is positive, then the entropy of the surroundings must be negative. And if the system is exothermic, it's releasing heat, then the entropy of the surroundings must be positive. And so I can start to relate this into a more concrete equation here, Gibbs free energy equation. Delta G, the change in free energy, is equal to delta H, the change in enthalpy, minus the Kelvin temperature times the change in entropy for the system. And what's wonderful about this is with this equation, I can keep everything system oriented and not have to worry actually at all about the surroundings. So we've done plenty of examples where we've measured the enthalpy change for a system. In Chem 105, we did a whole bunch of calorimetry. Calorimetry was used to describe the enthalpy of the system by monitoring how the temperature of the calorimeter changed, either positively or negatively. And we can measure entropy of the system in the same kind of way, not necessarily with a calorimeter, but we have other means of experimentally determining it. And so what this allows us to do is I can start to evaluate free energy based off of those measurable quantities around and about the system. Now, what does this have to do with spontaneity? Well, we have to start thinking about, well, what does it mean? Um, and so we get into the ideas of, we know that we want the entropy of the universe to increase. So positive entropy in either direction is what is needed for spontaneity. And so if I start looking at things here, based on what we saw about the entropy of the surroundings being related to the system, what I can start to see now is, okay, we definitely want system to be positive if at all possible. But if it's not possible to get the entropy of the system to increase, we need the entropy of the surroundings to increase, which means that we need an exothermic reaction. We need delta H to be negative so that the change of surroundings is positive. The two negatives cancel each other. And since this definition directly peels into this one, then what we start to see is that free energy the sign of our free energy tells us our spontaneity. So when delta G is negative, that is meaning the entropy of the universe is increasing, we get a spontaneous process. When delta G is increasing, when it's positive, delta S for the universe is negative, it's a non-spontaneous process. So with the use of Gibbs free energy, we can dissociate ourselves from having to focus solely on entropy. And we can focus on things like enthalpy and entropy to figure out spontaneity in a much more easily measured kind of fashion. And so we can rewrite and rethink the second law in terms of free energy. So the second law of thermodynamics says that the entropy of the universe is increasing for a spontaneous process. Another way of thinking that is that a spontaneous process has to have a negative free energy change. So the free energy of a reaction is decreasing, that reaction will be spontaneous. And so there are three possible interpretations of delta G overall. If delta G is less than zero, otherwise known as negative, then the reaction will be spontaneous. If delta G is greater than zero, otherwise known as positive, then the reaction will be non-spontaneous. And if delta G is actually in the middle and is exactly at zero, then what we have is the perfect blurring of the line between spontaneous and non-spontaneous, where both reactions are favored in equal and opposite directions. We felt that equilibrium from the start. So let's take a look at an example of this free energy reaction equation in use. So here we have nitrogen and oxygen reacting to form nitrogen monoxide. Nitrogen monoxide then reacts with oxygen again to form nitrogen dioxide. What we want to know is what is the value of the standard free energy change for this reaction at 298 Kelvin if our enthalpy of reaction and entropy of reaction are these. Now, just a quick note here. Notice that these all have the degree symbol on them. Don't get freaked out by that. That degree symbol just means that we are talking about standard conditions. That Gibbs free energy equation works at all conditions. But if we are at 298 Kelvin and 1 atmosphere of pressure, then we are dealing with standard conditions as well. So the Gibbs free energy equation, delta G is equal to delta H minus T delta S. We're trying to find delta G. We're told that delta H is negative 114.2 kilojoules. We're at 298 Kelvin. And delta S is negative 146.5 joules per Kelvin. Now, before we start furiously punching this equation into our calculator, like it's the case for a lot of the times where we have used energy equations this semester, we need to take special note of the units because it is very common and easy to see unit mismatches in our equations. So if I plug this in, I end up subtracting joules from kilojoules. If I didn't know that I had a difference there, it would show up. So before we go further with this, we need to fix the unit mismatch so that when I do the subtraction, I'm subtracting the same unit from each other. And which way that you go with this really doesn't matter. For me personally, I prefer multiplying to dividing. So I will fix my kilojoules and turn them into joules. So that the unit matches up here. You could have easily taken the joules per Kelvin and turned it into kilojoules per Kelvin by dividing by 1,000 as well. Again, that is a personal preference thing. That is not dogma. But working through the calculation, 298 multiplied by 146.5 is 43,657. So negative 114,200 minus 46,000 minus negative 43,657. rounded to the hundreds place, because that is our last significant digit here, we get negative 70,500 joules, which we could then turn into negative 70.5 kilojoules. So this reaction is spontaneous at these conditions because our Gibbs free energy calculation tells us that it is releasing net energy into the surroundings. And that's ultimately the fine test of whether a reaction occurs on its own or not. Is there net energy release or is there net energy input? All right, questions with this first example? Okay, so we need to introduce a little bit more new terminology. So for enthalpy, heat energy, we've talked about the idea of endothermic or exothermic. Endothermic for heat coming into the system, exothermic for heat leaving the system. With free energy, we have similar kinds of terminology. They have the same prefixes, X for exiting, endo or end for incoming, internalizing. But the terms that we use are slightly different. Instead of thermic terms, we're going to talk about gonic terms. Gonic terms are going to be which direction is the free energy going. Exergonic processes have a negative change in free energy. These are what we call spontaneous processes. Endergonic processes are those where energy is inputted. Free energy has to be input, which means that it is non-spontaneous in that direction. But like we talked about at the beginning here, just because it is endergonic in this direction, that would also mean that it is exergonic in the reverse direction. And so it would be the reverse direction that we would consider spontaneous. And so one thing that the Gibbs free energy equation really kind of puts home for us is that it allows us to explain some of those phenomena that wouldn't make sense alone. So for example, enthalpy. It makes sense to us from an energy releasing standpoint why an exothermic reaction would be spontaneous. But yet, we know that there are spontaneous endothermic processes as well. For example, ice melting at room temperature is an endothermic process. Heat has to go into the ice cubes. And yet it happens without interference at room temperature. Why is that the case? That doesn't make any sense from an energy standpoint. Until you consider that while the enthalpy might be positive and non-spontaneous leaning as a result, the entropy of the system is going to be such that it actually works. We're going from a solid, which is more ordered and has fewer degrees of freedom, to a liquid, which is less ordered and has more degrees of freedom. The entropy gained by the water molecules outweighs the energy gain that comes with the endothermic process. from a free energy standpoint, the entropy ends up winning and it becomes a spontaneous process. Why do precipitation reactions take place? On their surface, we would look at a precipitation reaction and say, well, hold a second. We have an entropy disfavorable kind of reaction. Two aqueous solutions coming together and making a solid? That doesn't make any sense. Entropy would be massively negative for that kind of circumstance. And yet it happens. Why does it happen? Well, for whatever entropy we lost, there must have been a greater gain in terms of the exothermic nature of that coming together. The exothermic nature of that reaction outweighs the loss of entropy. And so what the Gibbs free energy equation allows us to do is it allows us to quantify those kinds of scenarios. Because it's painstakingly obvious what's going to happen in certain scenarios. If I have a reaction where it is exothermic and gains entropy, I know it's going to be spontaneous because the enthalpy says that it's spontaneous, the entropy says it's spontaneous, it's going to be spontaneous. And on the flip side, I know that if a reaction has to take in energy and it loses entropy in the process, that process is not going to happen on its own. But for the ones that are in the middle, this is where the Gibbs equation really can help us, because it can help us to weigh those two conflicting ideas against each other. And so we can construct charts like this, where we actively compare the sign of the entropy and the sign of the enthalpy and make a determination over whether the reaction is spontaneous or not. So like I said, first condition, if it's favorable in entropy, favorable in enthalpy, it's going to be spontaneous. Doesn't matter what temperature we try to run it, it's going to react. It's going to be spontaneous. And meanwhile, if it's not favorable in entropy and not favorable in enthalpy, it's never going to happen. Doesn't matter what temperature we try to run it at, it's not going to happen. The tricky part comes in when the signs are the same. So if I have positive enthalpy, which is not favorable, and positive entropy, which is favorable, what I have is a temperature-dependent reaction, where at certain temperatures it will react and be spontaneous, and at other temperatures it will not react and be non-spontaneous. And what we'll find is that the same is true in the opposite. If I have negative entropy but exothermic, I'm going to find temperature dependence there as well. Now, the reason for the quotation marks there around high and low is because the terms high and low are relative. And what they're relative to is the equilibrium condition. In each of these cases, we could calculate a temperature where the reaction flips from being spontaneous to non-spontaneous, or vice versa. And so in the case of our third line here, high temps, what we're talking about is any temperature over that flipping temperature, any temperature that is higher than that, that's where we'll find spontaneity. Now, if the flipping temperature is at 85 Kelvin, that's a low temperature, at least on the scale, that's low. but we would still call it high if we measured it at 100 Kelvin, which is, negative 173 Celsius. Pretty darn cold. And the same is true for low. Low is just relative to that flipping temperature. So if the flipping temperature is at 1,000 Kelvin, 950 Kelvin would be considered a low temperature for that system. And the reaction would still be spontaneous. If I went to the other side, if 1,000 is my flipping temperature and I do the reaction at 1,100, it's not going to happen. So let's take a look at another example here. For a certain reaction, we have an enthalpy of negative 35.4 kilojoules and an entropy of negative 85.5 joules per Kelvin. Questions that we want to ask: is this exothermic or endothermic? Is disorder increased or decreased? And is the reaction spontaneous at 298 Kelvin? These first two questions we can answer just based off of the signs of enthalpy and entropy. So we have a negative enthalpy. By definition, that is exothermic. And since delta S is negative, that means that disorder is decreasing. So is the reaction spontaneous at 298 Kelvin? Only way to answer that is to plug in the values into the Gibbs free energy equation and see what the answer comes out to be. So delta G is equal to delta H minus T delta S. Delta H is negative 35.4 kilojoules. T is 298 Kelvin. Delta S is negative 85.5 joules per Kelvin. Again, we've got a mismatch here of units. So we need to change one of our energy terms into the other. Again, for simplicity's sake, I find it's easier to multiply by 1,000 than to divide by 1,000. 35,400 joules is the modified version of delta H. $298 times 85.5, negative 85.5 rather, is negative 25,500 joules. So putting those together, 35,400, negative 35,400 minus negative 25,500 is negative 9,900 joules, or negative 9.9 kilojoules. Delta G is negative. So that tells us that it is spontaneous. All right. Any questions about this example problem? All right. Gas phase reaction between methanol and water produce carbon dioxide and hydrogen. is accompanied by an increase in entropy under standard conditions. At what temperatures is this reaction spontaneous? Okay, we're missing a little bit of data here. We've got delta S for the reaction, but we don't have delta H. So the answer to that problem would mean that we need to find the relevant data here in our appendix tables and so we need heats of formation values for all of these, find delta H, and then we can move on from there. So for methanol, you go down to carbon, CH3OH in the gas phase would be negative 201. Carbon dioxide in the gas phase, since we're already at carbon, negative 393.5. And then go to hydrogen for water. Water in the gas phase would be negative 242. And hydrogen in the gas phase would be 0. And again, thinking about our definitions of heat of formation. Heat of formation is how much energy does it take to make this compound from its elements. If I'm already an element in its natural state, then it would require no energy to get me there. So delta H for the reaction is equal to products minus reactants. So 3 times 0 for hydrogen plus negative 393.5 kilojoules for carbon dioxide minus reactants, negative 201 kilojoules for the methanol, and negative 242 kilojoules for the water. So we've got negative 393.5 kilojoules for the reactants, negative 201 plus negative 242 is negative 443 kilojoules for the reactants. So delta H for the reaction would be positive positive 50 kilojoules. Okay, so now we have our thermodynamic data. We've got delta H of the reaction at 50 kilojoules. We've got delta S at 176.9 joules per Kelvin. How do we figure out the spontaneous temperature? Now, the answer to that question is a rather simple one. We need to figure out at what temperature it flips from being positive to negative. Because we know that negative is where things are spontaneous and positive is where things are non-spontaneous. What value lies between positive and negative? 0. So the trick to this is we need to set delta G equal to 0 and solve from there. And so if 0 is equal to delta H minus T delta S, if we rearrange that equation, T delta S is equal to delta H that temperature where things flip around is equal to the enthalpy change divided by the entropy change. Once again, we've got to make sure that we keep our units straight and tidy here. So 50 kilojoules into 50,000 joules divided by 176.9 joules per Kelvin. 50,000 divided by 176.9 to two significant figures would be 280 Kelvin. So 280 Kelvin is where things flip around. Now we need to interpret, when does it flip around? To what does it flip? So in this case, we are in line 3, positive, positive. This is going to be spontaneous at high temperatures. What does high temperature mean? Well, it means anything above that flipping temperature. So to answer the question, when is it spontaneous? When temperature is greater than 280 Kelvin. When our temperature gets above 280, that's when we know. Anything less than 280, it's going to remain non-spontaneous. At 280 Kelvin, it's going to be at some kind of an equilibrium. All right, any questions here? All right, let's try this one yourselves then. Very similar question to what we just did. We have a reaction where delta H is equal to negative 32 kilojoules and delta S is equal to negative 98 joules per Kelvin. Assuming that delta H and delta S do not change with temperature, where is delta G going to be equal to 0? So very similarly to the question that we just did, we can set up our Gibbs equation and setting delta G equal to 0. Even if we did not do all of the algebra in advance, we would still get to a spot here where negative 98 joules per Kelvin times T is equal to negative 32,000 joules. Divide each side by negative 98 joules per Kelvin. And from a temperature standpoint, since we weren't given a whole lot of precision in terms of our values, we only have 2 sig figs to work with. So we would have to round this to 330 Kelvin. Calculator says 326.5. So in reality, it's probably closer than that. But with what we're given, we can't do any more than estimate that. So 330 Kelvin is the flipping temperature. In terms of interpretation, this is a scenario 4 in that table. So when T is less than 330 Kelvin, we would expect it to be spontaneous. When T is greater than 330 Kelvin, we would expect it to be non-spontaneous. That's effectively what that interpretation means. All right, any other questions? All right, so last thing, and then we'll take a short break here. Like we have seen with enthalpy and entropy, there is a standard version of delta G. That's where we use the little degree symbol. And again, standard conditions, 1 atmosphere, 25 degrees Celsius, 1 molar concentration if it is a solution. And like we saw with the delta H calculation that we did a couple of slides ago, we can do the same kind of calculation using delta G, using thermodynamic tables like what we saw before. The thermodynamic table, in this case with the one that we've been giving you, delta G is the middle column. And what we'll notice is that, again, these are formation values. And what that means as far as formation is concerned is that since elements require no energy to be created from themselves, then the free energy of formation for an element is 0 so long as it's in its normal phase. If I have an element that's not in its normal phase, then it would have a non-zero value. But the calculation here, products minus reactants, would still apply, just like it did for delta H values using heats of formation back in thermochemistry in Chem 105, just like it did yesterday when we were doing delta S of reaction calculations using standard molar entropies from those thermodynamic tables as well. So just as a construct here, let's go through and do an example of these kinds of calculations using the free energy of formation values to do the calculation work ourselves. So we have water in the liquid phase. So that's negative 237 kilojoules. And then we have carbon dioxide. That's negative 394. And we have ethanol, C2O5, H5OH, and it is in the liquid phase also, so negative 175. And then finally, oxygen. Oxygen should be 0, and it is, because oxygen is already an element. So setting up the calculation, my free energy of reaction would be equal to the sum of the products minus the sum of the reactants. So on the product side, I have 2 times negative 394 kilojoules and 3 times negative 237 kilojoules. On the reactant side, I have negative 175 kilojoules for the ethanol and 3 times 0 for the oxygen. Putting together the two sides, 2 times negative 394 plus 3 times 237. I have for the products negative 1,499 kilojoules. And on the reactant side, I just have the negative 175. So putting those together, negative 1,324 kilojoules. So this reaction is very, very spontaneous, which shouldn't surprise you. It's a combustion reaction. In addition to being highly spontaneous, it's also highly exothermic, which is probably the main driving force there. All right, any questions here? All right, let's take a 10-minute break. So let's come back at about 10:20 or so. And we've got one more thing to discuss, and it's the relationship between free energy and equilibrium. And we'll cover that in the last lecture here.